Suppose the limit of a function exists. Say the limit of f as x approaches a equals L. If you could define the function to be equal to anything you want at x equals a, what would you anticipate f of a to be, and why? Would you be disappointed if somebody defined the function at a to be something like this, where what the function does at a does not match how the function behaves around a? Why would we want to plug the hole and define the function at a to match the limit as x approaches a, besides purely aesthetic considerations? Mathematically speaking, why would we want the function at a to equal the limit? What nice properties would we lose if we didn't define the function at a to be the limit? In pondering such questions, we're considering the issue of the continuity of the function at a. Before we proceed to answer such questions, let's define what it means for the function to be continuous at a. We say that f is continuous at x equals a if the limit of f as x approaches a equals the function at a. Notice that we are defining what it means for f to be continuous at a point a, not on an interval, but at a point. Let's unpack the statement that the limit of f as x approaches a equals the function at a. The single statement encapsulating continuity consists of three separate propositions. First, the right-hand side of the statement. For us to be able to say f at a means that f must be defined at a. If f is not defined at a, the function has no chance of being continuous there. Next, the left-hand side of the statement. For us to be able to write the left-hand side of this statement, the limit must exist. Recall that means checking that the two one-sided limits are finite and that they're equal. Finally, even if f is defined at a and the limit exists as x approaches a, those two must equal. They must agree before we have continuity. Let's look at graphs of four functions, all of which are discontinuous at a. In the first graph, the open circle indicates a hole in our function where our function is not defined. Since the function is not defined at a, our function is not continuous at a. The limit as x approaches a from the left and the right do agree though, so condition 2 holds. And the third condition for continuity automatically doesn't hold if at least one of the first two conditions don't hold. It would be absurd to ask whether the limit of f equals the function at a if at least one of those doesn't exist. In the second graph, the filled-in circle indicates that our function is defined at a, so the first condition for continuity is satisfied. But we see that in graph 2 the two one-sided limits do not agree, so the second condition fails to hold, and so our function is discontinuous at a. Condition 3 in a sense is irrelevant since you can't compare the function at a to a limit which doesn't exist. In the third graph we have a vertical asymptote, and the function doesn't exist at a, the limit as x approaches a doesn't exist, and the third condition is also not satisfied as it's nonsensical. If a function has a vertical asymptote x equals a, it cannot be continuous there, as by definition, for a vertical asymptote, one of the one-sided limits has to be infinite, so the limit will not exist. For the fourth graph, the function is defined at a, and the limit does exist as x approaches a, but even though those two exist, they are not equal to one another, so the third condition fails. Hence, the function is discontinuous at a. So finally, this new graph is a graph of a function which is continuous at a, as we see that f at a is defined, the limit as x approaches a exists, and furthermore that limit and the function at a agree. All three conditions are satisfied, so the function is continuous at a. Notice that if a function is continuous at a, and you are asked to sketch the graph of the function through a, you wouldn't need to lift your pencil in order to draw that, because the graph at a would be nice and connected in some sense. Compare that to the first four graphs in the bottom, where you would be forced to lift your pencil in order to sketch the graph. And don't at me about not needing to lift your pencil to sketch graph 1. You know what I mean. Let's briefly go over the concept of a discontinuity being removable. Consider the function f defined by sine x divided by x. The function is not defined at x equals 0, so our function f is not continuous at 0. However, we know by the special trig limit that the limit of our function as x goes to 0 does exist and is equal to 1. Because the limit does exist, we can define a slightly altered function. Let's call this function g, and it's equal to our old function sin x over x when x is not 0, but now we define it to be equal to 1 when x is 0. So now g at 0 is defined, it's equal to 1. The limit of g as x approaches is defined, it's equal to 1. And so the limit and the function at 0 agree. G is continuous at x equals 0. And this function g is exactly like our old function f, except where we removed the discontinuity at x equals 0. We've plugged the hole in the graph of sine x over x, so to speak. If the limit of a function as x approaches a exists, and the function is not continuous there, we can always alter it to remove the discontinuity. To reiterate, for a discontinuity to be considered removable, the limit of the function as x approaches a has to exist. To summarize, if f is discontinuous at x equals a, but the limit of f as x approaches a exists, then f has a removable discontinuity at a. We remove it by defining a new function which is equal to f of x everywhere except at a, and we define the new function at a to be equal to that existent limit. If, however, the limit of a function as x approaches a does not exist, there's a discontinuity there, and we say that f has a non-removable or essential discontinuity at a. Some discontinuities are tamer than others, I guess. Let's return to the question of why continuity is nice. I'll share just 2 reasons that are relevant to your first semester of calculus. The first reason is the Intermediate Value Theorem. To illustrate this theorem, consider functions which are continuous at every point on some interval from a to b, including the endpoints. So these 2 graphs reflect that continuity because the graph is nice and connected, loosely speaking. There are no breaks. Now, take any intermediate value, m, between f of a and f of b. Then we can conclude that there is a number c in the interval from a to b, such that the function at c gives you this intermediate value m. When we say there exists a number c in the interval from a to b, we mean there exists at least one such number. There could be multiple such numbers, as you can see from the second graph. One application of the Intermediate Value Theorem is to narrow down a range in which the zero of a complicated function exists. Suppose we have a function f, which is known to be negative at a and positive at b. Since f of a is negative and f of b is positive, we see that 0 is an intermediate value between f of a and f of b. Now suppose f is continuous everywhere on this interval, including the endpoints of the interval. We can conceptualize sketching the graph of this function in one nice connected movement. There are no breaks in the graph, no discontinuities. Then there must exist a number c in the interval from a to b, such that the function at that c is equal to 0. And that's a consequence of the continuity of the function on the interval from a to b, according to the Intermediate Value Theorem. So if f is a somewhat complicated function whose zeros we cannot solve for easily, we can at least narrow down an interval in which we know the 0 exists. Another reason continuity is nice is that continuous functions interact with limits well under composition. More precisely, if the limit of g as x approaches a exists, it's equal to some number b, and f is continuous at b, then if you want to take the limit of f composed with g as x approaches a, you can simply bring the limit statement inside this continuous function. As an example, suppose g is equal to sine x over x. We know that the limit of g as x approaches 0 equals 1. Let f of x equal the natural log of x. F is continuous for all positive x's, including x equals 1. Now take the limit of f composed with g as x approaches 0. Because log is continuous at 1, we can bring the limit statement inside our continuous log function. So we have log of the limit sine x over x as x approaches 0, so log of 1. Can you think of an example where this property wouldn't hold if f were not continuous at b? Computational examples will be worked in the next video.